Momentum, collisions, and the general form of Newton's second law of motion are few of the subjects that we will discuss in this vlog of the classical mechanics mini-series. Now let's start with momentum. Momentum is the quantity of motion of a moving body. Basically, the more momentum an object has, the harder it is to stop. Now, let's give an example for you to understand it better. In the example in the whiteboard, we can see a person that's trying to catch two different baseballs. The first time, the baseball has a speed of 2 meters per second. And the second time, the baseball has a speed of 10 meters per second. Now imagine yourself to be that person. You would really hope to lose that game rather than catching the baseball in the second time. Now let's pass to the definition of momentum. In physics, we use the mathematical formula that is written on the whiteboard in order to describe the concept of momentum. As you can see in the whiteboard, momentum is a vector quantity and equals to the product of mass and velocity. Since momentum is a vector quantity, it has the magnitude of the product of mass and the magnitude of velocity, and direction, the direction of velocity. For the next part of our video, we have the general form of Newton's second law of motion. In the first part of our classical mechanics mini-series, we learned the second law of motion by Sir Isaac Newton in its simplest form. Today, now that we have already found out what is momentum, we're going to use the constant of momentum in order to find the general form of Newton's second law of motion, which is as it's depicted on the whiteboard, that the total forces equal to the change in momentum over time. And it's followed by the explanation of the simplest form of Newton's second law of motion. We differentiate the momentum over time, but because mass is constant, it goes out of the differentiation, and we have then the mathematical formula that we learned in our first part of the classical mechanics mini-series. Now that we have understood the general form of Newton's second law of motion, we can understand the conservation of momentum principle. And what this principle says? It says that in an isolated system, the total momentum of the objects before the collision equals to the total momentum of the objects after the collision. What that means? Here on the whiteboard we have the mathematical formula, which I'm going to explain. If the total external forces are zero, which means that the system is isolated, the change in momentum is also zero. That means that the momentum is constant. So the total momentum before is equal to the total momentum after the collision. Now let's move on to collisions. As you can see in the whiteboard, there are two major categories of collisions, and with two subcategories each. The first category of collisions, as you can see, it's about the dimensions of collision. We have the first category, that is head-on or one-dimensional collisions, and the non-head-on or the two-dimensional collision. In this category, the speed of the particles in the collision are not in the first category, just in the one axis, and in the non-head-on collisions are in two axes. The second category is about what happens at the energy during collision. The first subcategory, which is elastic collisions, means that in elastic collisions, energy does not get lost during the collision. But in the second subcategory, there is a loss of energy during the collision. And now, for the last part of our video, we're going to analyze the variable mass systems. So, with the simplest form of Newton's second law of motion, we could only analyze systems that their mass was constant. But now, with the general form of Newton's second law of motion, we can study systems that mass changes over time. As you can see in the whiteboard, at first we have the general form of Newton's second law of motion. Then we do the differentiation, but now since mass is not a constant but it changes over time, the differentiation equals to the change of mass over time multiplied by the velocity plus the product of mass and the change of velocity over time. We have a mass that changes over time, and we want to find the equation that governs this change. We only have the rate in which the mass changes over time, which is a positive or negative constant. So, if we follow the process that we did on the first part of our classical mechanics mini video series, through separating mass and time variables and integrating, we can finally find out the equation that governs the change in mass over time. I hope you liked this video. If you did, subscribe to our channel for more videos like this. Also, you can like, share and comment on this video. You can also follow us on Facebook and on Twitter, and the links are below in the description. Thank you again, and see you in the next episode of A Journey into Physics.